Electromagnetic waves are sinusoidal, as we've seen, and the direction of the electric and magnetic fields are perpendicular to the direction of motion and perpendicular to one another. You'll recall that we talked about, let me show you what we had earlier. We talked about the relationship between the electric and magnetic fields and the direction of motion, and this diagram here on the right shows that relationship. Notice that each is sinusoidal. This is a natural consequence of electromagnetic waves. They are sinusoidal. The electric and magnetic fields are sinusoidal in their variation in time along the time axis and in space along the space axis. Here in this particular diagram we show the waves as a function of x. So this is a snapshot of an electromagnetic wave as seen along the x-axis at a particular moment in time. The whole thing is moving to the right with velocity v. Now, in order to capture that sinusoidal shape, we can express the electric field along the y-axis, in this particular case, as an amplitude E naught times the sine of this argument, 2 pi times x over lambda minus t over t, capital T. Let me just say what these are. Lambda here is the spatial wavelength, the wavelength of the wave, which you've learned about previously when you talked about waves last semester. So lambda is the wavelength of the wave. Capital T is the period, how long it takes for one full cycle of the electromagnetic wave cycle. X, on the other hand, is a variable. It's the variable along the x-axis, and t is the time variable. Now, we won't go into detail as to why this is the expression. We could, in principle, but it will detract from our main focus, and that is that the electromagnetic wave consists of a sinusoidal electric field component. Here's the sinusoidal function, and the argument of that function, 2 pi times x over lambda minus t over capital T, is tells us how the wave is laid out in time and in space. The important points here are that we're talking about the electromagnetic wave in the y direction. It has a total amplitude of E naught, the maximum that it will be, and it's modulated by a sinusoidal function. Likewise, the magnetic field in this particular case is oriented along z, which is perpendicular both to the direction of motion and to the electric field, and it is equal to a amplitude b naught times the same sine function. Okay, let me just show you this diagram again. You'll notice the waves have the same basic wavelength and the same frequency and the same shape. They're both sinusoidal waves. So this is the way we describe electromagnetic waves in terms of the sinusoidal functions that they that describes the way they behave. And E naught and B naught are the amplitudes. Knowing that, we can calculate. We've learned that the ratio of the strengths of E and B is the factor C, and knowing that, we can talk about the relationship between the amplitudes and the intensity of the wave. The energy of the electromagnetic wave, all waves carry energy, and the electromagnetic wave is no exception. What propagates through space is actually a form of energy in the shape of electric and magnetic fields. And the energy of the electromagnetic field depends on the amplitudes of the electric and magnetic fields. In chapter 15 from last semester, you learned that the intensity of a wave, or the intensity of something that has power spread out over area, is defined as the ratio of the power to the area. It's in watts per square meter. I believe you talked about sound waves last semester as having intensity, and the sound wave has a certain amount of power that's propagating through space, and it's spread over an area A. So we have the same situation here. We have the intensity of a light beam is going to be the power of the light wave, or the energy transferred per second spread out over an area A. And the way that we express that mathematically is as follows. First of all, the definition of intensity is power over area. The power of an electromagnetic wave divided by the area is equal to 1/2 c epsilon naught E naught squared. This is presented without proof, but here is the expression for the power density, or the power per unit area, for an electromagnetic wave. 1/2 c epsilon naught over E squared times E squared. And knowing that E naught and B naught are related by a factor of c, that also translates into 1/2 c over mu naught times B naught squared. Again, these are presented without proof, but they are given to you in order for you to be able to calculate the intensity of an electromagnetic wave, if in fact you know the amplitude E naught or B naught, or conversely, if you don't know E naught or B naught, but you do know the intensity of the wave, you can calculate those quantities from the intensity using this formula. Let's actually work out a problem having to do with this. Okay, so in this particular problem, and this is, by the way, very similar to number 27 from your chapter, which is one of your homework problems. Inside the cavity of a microwave oven, the 2.4 gigahertz electromagnetic waves have an intensity of 5 kilowatts per square meter. So 5 kilowatts spread over 1 square meter represents the intensity of this particular electromagnetic wave in a microwave oven. And the question is asked, what is the strength of the electric field and the magnetic field as well? So let's start from an expression of the intensity related to the electromagnetic, the electric field, excuse me. I is equal to C epsilon naught E squared over 2. C epsilon naught E naught squared over 2. And so we can solve for the electric field, which is the square root of 2I over C epsilon naught. And if we plug in our numbers that we're given 2,500 watts per square meter for the power. We know the speed of light, and we know epsilon naught. So we can calculate from these what E naught is given the intensity of the wave. And it's 1.4 times 10 to the 3 volts per meter, or 1,400 volts per meter. This is what exists inside the microwave oven if its power is 5 kilowatts per square meter. And then to calculate the magnetic field, we simply associate its relationship with the electric amplitude E naught. The two differ by a factor of C. So if we divide E naught by C, we find out that the magnetic field is 4.6 times 10 to the minus 6 Tesla, or 4.6 microtesla. I also wanted to say a few more words about polarization. We've looked at this slide in the previous video, and this slide simply shows us the effect that a polarizer has on unpolarized light. We have unpolarized light coming into this polarizer, and what survives is the light that is aligned along the polarization axis. Notice the polarization axis is perpendicular to the polymers, or the long molecules, because the axis perpendicular to them is the axis that lets light through and does not absorb it. Light that's vertical in this particular case is absorbed by the polarizer, and light that is horizontal is passed by the polarizer. Let's think a little bit more about that. When polarized light approaches a polarizer, the magnitude of the electric field of light transmitted is going to be the incident intensity E times the cosine of the angle theta. You can see that from this diagram here. So first of all, we have an electromagnetic wave that in this particular case is polarized at angle theta relative to the polarizer axis. Remember, the polarizer axis is the axis corresponding to the polarization of light that is allowed through the polarizer. It's what is passed through the polarizer. So the polarizer axis here is vertical, meaning that it's only going to pass light that is vertically polarized. Now you'll notice that the light that is coming into this polarizer, denoted by this vector at angle theta to the polarizer axis, has a certain amplitude. And geometrically, that amplitude has a certain component along the vertical axis. Sorry, I didn't draw that very well. You see a triangle here, and you see that the projection of E onto that polarizer axis is going to be E naught times the cosine of theta. So, when I have a beam of light that is plane polarized encountering a polarizer, if there's an angle theta between the direction of polarization of the light and the transmission axis or polarizer axis of the polarizer, then the surviving amplitude is going to be E transmitted, which is the incident amplitude times the cosine of theta. And since cosine theta is at most 1, it's going to be a fraction of 1. A fraction of the light will survive. If the polarized light is parallel to the polarizer axis, it will pass the entire beam because theta is 0 and the cosine of theta is 1. Likewise, if the light is perpendicular to the polarizer axis, it will be entirely absorbed because there's no component along the polarizer axis. So let me just depict this briefly. For this particular polarizer, if I had a beam with its electric field vertical, then it would be passed entirely. If I have a beam of light that is entirely horizontal, it will be absorbed by this polarizer and therefore won't pass. Now there is an equation we can use to calculate the transmitted intensity. We just learned that the electric field is diminished by a factor of cosine theta if its axis is not completely aligned with the polarizer, and so the intensity is proportional to E squared, as we just learned, and therefore the transmitted intensity of this beam is going to be the incident intensity times the square of cosine. This is called the law of Malus, or Malus. I'm not sure whether the S is pronounced or not, but anyway, the law of Malus captures the idea that the intensity of the beam surviving the polarizer depends on the angle between its polarization axis and the polarization axis of the polarizer. And so we have this law that allows us to calculate the intensity of a beam as it encounters a polarizer. Now, you can use a polarizer either to polarize light or to analyze light. And here we've got two polarizers, one of which is serving as a polarizer and one of which is serving as an analyzer. The way we produced polarized light is by sending natural or unpolarized light into a polarizer that's oriented at a particular axis, along a particular direction. And so since this is the axis of polarization, what survives is going to be plane polarized light, which is going to have its polarization in the direction of the polarizer axis. So we go from natural light to polarized light, and then we can assess that polarized light using an analyzer, which is really nothing more than a second polarizer. And that's the one that's going to tell us which direction the polarization is. For example, in this particular orientation, you can see that the two are not exactly parallel. The polarizer and the analyzer have an angle theta between them. And so what's going to survive the analyzer is the amplitude of this intermediate wave times the cosine squared, or, well, the intensity of the intermediate wave times the cosine squared of the angle between the two polarizers will give us the final intensity of the beam that finally leaves. So we have unpolarized light being translated into polarized light with a certain amplitude, and that amplitude is going to be cut down by the cosine of theta, or the intensity of that intermediate wave will be cut down by the cosine squared of theta, according to the law of Malus. We can demonstrate this using a pair of polarizers, one of which will polarize unpolarized light, and then the second one which will analyze that. If the two polarizers, the polarizer and the analyzer, have their axes parallel, then you'll notice the light is transmitted. It's this portion right here that overlaps those two. That portion is transmitted because the polarizer, this one, and the analyzer, this one, are parallel. If they have an angle between them, you'll notice that the light that passes through both is going to be diminished in amplitude. It's darker because the light that is passed by the polarizer is slightly reduced by the analyzer because the two polarizer axes are not parallel. In fact, in this particular case, they're 45 degrees apart. And finally, if we rotate the analyzer a full 90 degrees relative to the initial orientation, you can see that no light passes. In this particular case, the light that the polarizer passes is perpendicular to the light that's transmitted or allowed by the analyzer. You can see the axes right here and right here of the polarizer and analyzer, and you can see that they're perpendicular. So when they're parallel, light passes completely. When they have an angle between them, light passes diminished by a cosine squared factor. And then when the two polarizers have their polarization axes perpendicular to one another, no light passes, which is evidenced by the fact that it's black. The amount of light coming through is black, and therefore we see that we can block that polarized light by orienting those axes. If ever you wanted to figure out what the direction of polarization of polarized light was, you could simply take an analyzer and rotate it until you see maximum transmission. And when you see maximum transmission, that is the time when the polarizer axis is aligned along the plane polarized light and passes it with 100%. And if you rotate it 90 degrees to that polarization axis, you find that the analyzer blocks the light and you get no transmission.